Hello everyone, I'm sorry for taking a lot of time to do a new video. I was very busy with work, so I come back with this new idea about why wireless communications are not done with satellites. I will use this document, I will read it to argue that wireless communications are more efficient if they are done with ground-based towers instead of geostationary satellites. So I have considered three types of wireless data transmissions: phone, TV and internet. If you think about the wireless data transmission systems which are used everywhere, they are composed of transmitters and receivers. So there are two ends involved. One of them transmits data and the other one receives. Based on the flowing direction of data between any two communicating ends, we can split these systems, wireless systems, into the following two categories. So we have the first category, one-way only flowing of data, which means one end has a transmitter and the other end has a receiver. And two-way flowing of data, which means both ends have a transmitter and a receiver, and they can truly communicate to each other. For a one-way only transmission, such as TV, the following schema illustrates how the system should work. So we have in the middle here the red square, which is a transmitter, and placed around it at different horizontal distances we have a set of receivers, which are represented by blue squares. The dotted red circles are the area of the maximum distance, the distance of the transmitter signal. We can observe that some of the receivers are hit by these signals and some are not, because they're outside the maximum distance of transmission. Okay, so I already said this. In the case of this system, the transmitter sends data continuously without being able to know how many receivers there are around which receive the sent data. If the transmitter wants to have any chance to know how many receivers are getting the signal, a two-way transmission is necessary. Okay, so this is how a one-way only transmitter works to provide, for example, television wireless transmission. While the one-way transmission system is valid and sufficient in order to have a wireless TV network, I will argue why this is not the case nowadays in our societies. And the answer is simple: because the television networks know exactly how many clients there are which are receiving their signal in order to calculate their ratings for each individual channel. So they can't do this without a two-way transmission system. In order to describe how the two-way transmission system works, we'll have to analyze the communication networks which can't exist without this type of system. For example, phone and internet, because this is about communicating with each other, not just receiving data and not caring who receives it. I will illustrate this two-way system between two ends in the following schema. So here we have two clients, and in order to communicate with each other, client A, any one of these two clients, transmits first a request to establish communication with another client. I've named it client B, and then after receiving the communication request, client B transmits back the response to client A. So this is how basic two-way transmission works, with requests and responses. Although this representation of a two-way transmission system is valid, there are some problems with it when it comes to the efficiency of data transmission matched against the safety and financial costs of the individual human client which uses it. Each transmitter needs to be extremely powerful in order to be able to send the data at longer distances. So if you have isolated clients, they need to have a lot of power in their transmitters to cover longer distances. As the required distance of transmission increases, the power of the transmitter needs to increase as well. This is obvious, okay? The cost of more powerful transmitters and the increased radiation levels which affect the human user make this particular organization of the system non-feasible. So this is less efficient as a two-way transmission system. And that's why the second way to achieve this kind of transmission between clients is to have the most powerful transmitters as intermediate nodes in the network, while keeping the client devices, which are less powerful, as ends. So the intermediate nodes would become transmission towers, in this case, and the ends would become cell phones or internet routers. The following schema illustrates how the two-way system should work between two less powerful transmitting ends, while having intermediate and more powerful transmitting nodes to pass the data at longer distances. So we have another schema. The red squares are this time intermediate nodes, transmitting towers, which are more powerful than the client ends, which are the blue squares. The maximum range of the blue squares is smaller, okay, and we can observe that the intermediate nodes communicate with the clients around them and at the same time communicate between each other. The blue squares, which are filled with the color blue, are the ones which have established communication with the towers because their signal touches the receivers of the towers. The other client ends are outside the coverage area of the towers. Okay, so I already said that the red squares are intermediate transmission towers which use either focalized, which means not spread everywhere around, wireless transmission signals, or cables to communicate with other similar towers. This communication between towers is represented by the red dotted lines between the two red squares. And which at the same time use spread wireless transmission signals around them to communicate with client ends. So this is how I imagine this kind of communication system to work. Now, the maximum distance of communication thus becomes the minimum between the signal distance of the client end and the signal distance of the tower for reaching its clients. So the maximum communication distance is the minimum between the radius of this blue circle and the radius of this red circle. Okay? Because even if the tower has a larger distance, coverage distance, he needs to receive back information from the client in order to be able to communicate. Okay, so for the schema above, it can be observed that communication is possible when the blue dotted circle touches at least one of the communication towers. With such a network system, the distance is no problem for wireless communication between two client ends, because the towers pass between themselves the signal until it reaches the desired client end target, a thing known as signal bouncing. As a consequence, the cost and functional capability of the client end devices for the blue squares are as small as they can get. So the cost and functional capability of the client devices are as small as they can get, which is very efficient and feasible. After agreeing that this is the most efficient way for the internet and cell phone networks to be organized, we need to analyze the differences between having towers as intermediate transmission nodes and satellites. So I have discussed three main points about this comparison. The first of the points, we need to investigate the maximum wireless communication distance between an intermediate node and its client ends in each of the two cases. Information about geostationary satellites can be found on these pages. Geostationary orbit, okay, at what height mainstream science says that it's available, and then information about the stratosphere above which the satellites are claimed to orbit, or in this case just stand still, because they need to be geostationary in relation to Earth. So these are pages with information about this. Maybe there are others. So if you read these pages, you will understand that the supposed altitude of geostationary satellites is around 35,000 kilometers. Okay. And if you try to do a little search about the altitude where the height of about the height of a ground tower, you can come across the following parameters: from 100 to 500 meters. Towers are not very high. They are around a few hundreds of meters high. So now we use the following schema to understand and reveal what is the maximum horizontal distance for wireless transmissions in each of the two cases, ground towers and satellites, while considering transmitters of equal strength. If you mount a transmitter of a particular strength on a satellite and on a ground tower, we will investigate what is the maximum horizontal distance which the transmitter covers. Okay, so a transmitter, as I've said, which interacts with its clients, will spread the signal at the same maximum distance in space all around it. In this schema, we have the transmitter as a red square. It is at the height denoted h, with this letter h. It transmits at a distance, at a maximum distance of x kilometers. This is the capability of the transmitter, the distance in space. And d is what we're trying to deduce. It is the horizontal distance of the horizontal distance of the signal which is received by the clients. We can observe that there is an obvious constraint for the x distance, which is the distance in space of the transmitted signal. It needs to be greater or equal to the h distance, to the height, because we have here a right angle between h and d. So assuming that the maximum signal distance in space for the transmitter is equal to the altitude of a supposed geostationary satellite, in this case 35,000 kilometers, but I doubt that there is a transmitter this powerful in existence. So using this, we get the following horizontal distances in each of the two cases. So for the satellite, using the Pythagorean theorem, we reach the horizontal distance of 0 kilometers. So the client needs to be exactly under the satellite in order to catch the signal. And for the tower, which is at the height of half a kilometer, we have considered, the horizontal distance is... Oh, I forgot to square this. Well, wait a minute. I don't know how I oversaw this. Okay, so we square this 35,000. So we have the horizontal distance of the horizontal distance in the case of the ground tower, it is approximately 35,000 kilometers, which is way larger than the distance covered by the satellite, the horizontal distance covered by the satellite. So having these results would render one completely irrational to believe that a satellite covers a bigger horizontal distance than a ground tower would. So using this formula, simple formula, you can deduce what is the horizontal distance for transmitters placed at different heights. We can deduce from this that as closer to the ground the transmitter is, the longer the horizontal distance coverage of the signal will be. So it is more efficient and more useful to have the transmitter closer to the ground, because the clients which are served by that transmitter are on the ground. The second point, but the first point should be quite enough to understand that ground towers are the best choice for having a wireless network system. But let's discuss the other 2 points. Nonetheless, the second point, there is no difference between satellites communicating with each other when it comes to bouncing signals and ground towers communicating with each other if their communication is done via focused wireless signals. So independent of the height of the transmitters, when bouncing signals, the horizontal distance of communication between such intermediate nodes is the same. So there is no difference between satellites and ground towers when it comes to bouncing signals. But if cables are required to cover distances which the best wireless transmitters can't cover, then the existence of satellites is downright impossible, as binding satellites with cables is not feasible. As a conclusion for this second point, the ground towers are equal or more feasible and efficient than supposed satellites. The third and final point, the cost for the existence of satellites instead of ground towers is clearly larger. The transmitters which are attached to these nodes can be powered with solar panels indeed, but geostationary satellites need some form of propulsion system in order to be kept constantly at the same altitude, like jet force or propeller force. The ground towers, on the other hand, rest on the earth, so they don't need any energy to generate the propulsion needed to keep them at the same altitude. Therefore, the ground towers win when it comes to maintenance expenses. Therefore, having analyzed the pros and cons of satellites versus ground towers, it is obvious beyond any doubt that ground towers are the best way to have an efficient wireless communication network, even if geostationary satellites would be real, which I can argue that are not. Thanks everyone for watching.